Hello everyone, today's topic is Favorskii rearrangement. So let's start. Here you can see the substrate for this rearrangement. At alpha position with respect to the keto group, we have a leaving group. Now mostly this leaving group is halogen, but there may be some other types of leaving group. So better we represent it as leaving group. Okay. So 1, 2, 3, 3 carbons I have numbered. So first, in presence of this base, that is ethoxide, ETO minus, there will be removal of hydrogen. Now this hydrogen will be removed, there will be negative charge generation and it will attack at this carbon where the leaving group is already present, and you will get cyclopropanone intermediate. Now this intermediate is symmetrical, but still I have given this number so that you can understand that two types of bond breaking possible, right? So this OAT minus, now when it is attacking at this carbonyl carbon, either 1,2 bond will be broken or 2,3 bond will be broken. So when 2,3 bond is broken, you will be getting the second product, and when 1,2 bond is broken, you will be getting the first product. Though both are same, but still we have this, it is better we see it in this way, because when the cyclopropanone, it will not be symmetrical, you will be able to understand that these two products will be different. And in that case, the question of major minor arises. Here, both are same. So let's take another substrate where cyclopropanone intermediate, it is not symmetrical. So see, if you break 2,3 bond, the negative charge will be at 3 position. If you break 1,2 bond, the negative charge will be at 1 position. Which carbanion is more stable? Obviously the carbanion where methyl group is not giving its plus I effect. So that is why this will be the major product where negative charge is on 3 carbon. We will obviously see the mechanism in detail separately, but here just try to understand why this compound, this product is the major. Now some more informations regarding this information. What is this Lg? This Lg mostly when it is halogen Cl or Br, or it may be tosylate, mesylate or triflate. These type of leaving groups can also be possible. Now bases, what type of bases we can take? Here the in these two examples you are seeing ethoxide is the base, and that is why the product is A star. So see, all these products that you are seeing here, they are A star. But suppose you have taken NaOH or KOH, in that case it will be carboxylate salt. So in this here you can see CO2 ET, and in that case what you will see COO minus, something like this. Now as the medium is basic, so that is why carboxylate salt, better we say carboxylate salt, because ultimately after workup it will be converted to COOH, that is final product will be some acid. And if you are using amine in the second step, then your final product will be amide, because in that case it will be CONH2, right? Now we will see the mechanism. Okay, fine. The overall result, an alkyl group is transferred from one side of the C double bond O group, that is carbonyl group, to other side. Now what it actually means? It actually means, see in this example, 2 carbon is the carbonyl carbon. One side you have 1 carbon, another side you have 3 carbon. But after reaction, see, both 1 and 3 are on the same side of 2, isn't it? Both 1 and 3 are on the same side. Same is also for the second compound, second example. So this is the overall change that is happening, that is written here as overall result. Alkyl group is transferred from one side of carbonyl to other side. Mechanism. So in this mechanism, the Lg is Br, and this carbonyl group, this substrate, if you see properly, here you have 2 different types of hydrogen. But obviously we will be focusing on this hydrogen, because when you consider the enolate which is generated by removing this hydrogen, so if you remove this left hand side hydrogen, you will be getting the first enolate. If you are removing the second hydrogen, you will be getting the second enolate. But only from the first enolate the cyclopropanone generation is possible. So we are not interested in this, though this enolate, that is another possibility. So our interest will be only on this enolate, right, where from you can get the cyclopropanone. Now this OAT, when it is attacking A and B, 2 different colors I have used so that you can understand 2 different possibilities for bond breaking. So if you are breaking the bond A, negative charge will be at this position, which will be getting this plus I effect of methyl, and ultimately it will be unstable. So if you are having any issue related to carbanion stability, if you want to know in detail, you can click on the playlist link right now on the top right corner, where you will get all the carbanion related videos. So B bond is, if it is broken, now the negative charge will be at this carbon, and here you will be getting this product, right? So when A bond is broken, here we will be, sorry, the negative charge is here. This will be the product which you will get from A, and if you break the bond B, that is this bond you are breaking, you will be getting the major product, which is this one, right? Next we will see the proof of cyclopropanone intermediate. The first proof, cyclopropanone intermediate has been trapped as an adduct with furan. So when we have that is this type of cyclopropanone, see what is happening here. This double bond, it will be attacking here. This CC bond will be broken, it will attack here, and ultimately this double bond will be shifted here, and you will be getting this type of product. So this formation of this, that is, if you just add furan in the reaction medium where you are suspecting this type of cyclopropanone, and if you are getting this final product, that means obviously this cyclopropanone is present. That is the proof, right? The second proof, two isomeric alpha chloroketone gave exactly the same product. So here, if you consider the left hand side compound, this negative hydrogen, if it is removed, negative charge will be here and it will attack this carbon and chlorine will be removed. You will be getting this type of cyclopropanone. And if you consider the right hand side substrate, then negative charge is here and you will attack here. You are getting same type of cyclopropanone. Now here it is not symmetrical. So if you break this bond, negative charge will be at that carbon and that will give you the major product, because this negative charge is stable because of resonance with pH, and ultimately you will be getting this product. So from both different types of, that is isomeric alpha chloroketone. So this is one isomer number 1, this is the second isomer number 2. So from both, when you are getting same product, that proves this type of cyclopropanone intermediate must be involved. The third one, leveling experiment. Here if we mark this carbon, suppose 14 carbon it is, then the cyclopropanone intermediate that will be first generated, it is like this, where this carbon is marked. Now two different types of product we will get depending on which side the CC bond is broken. So two possibilities are there. So see here the marking is here, here the marking is at the carbon, this carbon. So two possibilities. So if you are breaking the left hand side CC bond, then you will be getting the second product, and if you are breaking this side, then directly that is the first product you will get, right? Examples and synthetic applications of Favorskii rearrangement. Ring contraction, that is the most important, we can say one of the most important synthetic application of this rearrangement. So first in this, here this is the position where carbon will be generated, Br will be removed, and here we are using OH so that you can see some variation. This OH will be attacking at this carbonyl carbon, negative charge over oxygen. Now depending two different possibilities A and B, but we will prefer the bond breaking, which is B, because if you do so, then only you will get negative charge at the carbon where just beside pH is present, and it will make it stable by resonance. Okay, final product from 6-member ring we are getting 5 members. So this is a ring contraction, and see after you will do workup, so that is why ultimately it will not remain in CO2 minus form, it will be CO2H. Now one more one interesting example of ring contraction, as you can see here how the ring is contracted. First we are using base, then some proton source must be there so that we can convert the carboxylate salt to CO2H. So final product is some acid. Here we are using OH minus, not OET minus. So that is why ester is not the product. Cyclopropanone intermediate from ketene. So here the cyclopropanone that you are seeing, that we have not generated from any halogen substituted ketone. We have generated it from some ketene. So why this type of examples, it is important for us to understand, because sometimes in exam the Favorskii substrate, that is mostly the substrate we see in books, that may not be given directly. Suppose some other substrate is given, and from the reagent you have to understand how you can approach the Favorskii. So here you are getting the intermediate. Sometimes it may be also the generation of the substrate alpha haloketone. So in this case directly we are reaching the cyclopropanone intermediate, and that is from ketene by using either diazomethane or CH2I2Zn copper, which is basically Simon-Smith reaction. And then from the cyclopropanone, as you know, this OMe will be attacking here. Now this bond will be broken because the negative charge will be generated at this carbon which will be more stable, because if the negative charge is generated here, 2-methyl group, it will make it stability will be disrupted. Okay, so in this way we are getting this product. Cyclopropanone intermediate we are using, that is we are getting from ketene by some other reaction, and then Favorskii, but there is no alpha haloketone. The third example, dihalo substituted ketone. So until now you have seen single halogen, but there may be dihalo. Now see, two different types of dihalo we have. This is geminal type, that is same carbon you have two halogen. Negative charge will be generated here, it will be attacking here. You will get this type of cyclopropanone. Now for the second substrate, two different possibilities are there, but the approach of base for this hydrogen, it is better, that is sterical less hinder. So negative charge is, if it is generated here, you will be getting the same intermediate. Suppose if you are thinking about the other possibilities, suppose if you are generating the negative carbon at the left hand side carbon, in that case this should be your intermediate. Now this is not common intermediate, but if you see the full reaction, ultimately from this intermediate, even if it is minor, it will also give you the same product. So in presence of RO minus, it may be MEO minus or OET minus. Here we are having the next, you can understand how it is happening. Finally, this O negative, if it is making C double bond O, what will happen? This CC bond, that will be now shifted to this, and ultimately CBr bond will be broken. The same type of product you can also get from this. You can try it yourself. What will be the mechanism? So ultimately we are getting alpha beta unsaturated ester, right? One more type of dihalo compound you can get, where both the bromine, they are on the same side of CO, just like the first case. This is number 1 case, number 2 case, number 3. So here also both are on the same side, but they are not connected to same carbon. It is not geminal, it is vicinal, right? Now negative charge is here, bromine is removed, you are getting the cyclopropanone derivative, right? Now the RO minus, after the attack to carbon, the negative charge over this oxygen, what it will do, when CO bond is formed, this CC bond, sorry, not this one, this CC bond can be shifted here, and ultimately bromine is removed. So what you are getting? You are getting again CC double bond, unsaturation and ester, but it is not alpha beta unsaturated unlike the previous case, right? So that is the difference. In both cases you are getting some CC double bond on one side of ester, but one is alpha beta unsaturated, another one is not. Dihaloketone substrate you can also make starting from enone. So this type of dihalo compound you have just seen in the previous slide. Now this compound you can make starting from some enone. We are using bromine CCl4, where bromination will be happening to this CC double bond alkene, and then as usual Favorskii, you know. So you can try it yourself how we can, that is writing the full mechanism, it will be a good practice for you. So how we are getting this final product. Next example, haloketone substrate we are making from this ketone. So this is our Favorskii substrate, right? But that you can, suppose this is not directly given in the question. Suppose this substrate is given, and then this is the number 1 reagent, this is the number 2 reagent. So this will not be given to you. First you have to write it yourself, and then you can do the normal Favorskii. So that is why I am discussing this variation of examples, so that if it is not directly given, then also you can do it. So in presence of bromine acetic acid, first there is halogenation at this alpha position, and then our substrate is ready for Favorskii. You can do the normal Favorskii, right? This is also example of ring contraction. Very interesting example, isn't it? Preparation of cubene 1 carboxylic acid. So here see, this is also how ring contraction is happening. This is 5-member ring. In presence of OH minus, first this type of cyclopropanone intermediate you will get, and finally in presence of OH minus and some proton source, you will get carboxylic acid, cubene 1 carboxylic acid, right? And see, now it is 4-member, that means ring contraction is happening. The 7th example, from keto allyl halo substrate. So this is keto, then there is allyl group, then bromine is also there. So in presence of RO minus, you know how there will be negative charge. Now this negative charge, there is no halogen, but this CC double bond can be shifted here, and finally bromine is removed. So you will be getting this type of intermediate. Finally, when OR is attacking here, two possibilities A and B. Now if that is you break A, then just try both of them. Here directly I have shown this example, because if you break B, what will happen? So this negative charge is here, C double bond O. This CC bond, now it is shifted here. Sorry, let me do. So this just, so here B bond will be broken and negative charge will be generated at this position. Because if the negative charge is generated at this position like this, that can be stabilized by this type of resonance. Okay, so that is why negative charge generation is favorable here. But ultimately after taking proton from during workup, you will be getting this product as the major product. So these are the different examples and synthetic applications of Favorskii rearrangement. In the next video, I will discuss some stereo specificity and some other types, that is quasi-Favorskii rearrangement, etc. But that I have not discussed here. It will be unnecessarily lengthy. I will do it in the next video. So I think after watching this video, we will get some clarity on Favorskii rearrangement. Thank you for your precious time.